In this video, we're going to define resistance and talk about Ohm's law, which is in chapters 28.5 and 28.6 of the textbook. So in the last video, we talked about resistivity and conductivity. So now if we have a wire, well, in a wire, if we want to know the potential difference along a wire, well, that's going to be the current times the resistivity of the material divided by the length of the wire, or times the length of the wire divided by the cross-sectional area of the wire. So we can use that to define resistance. So for resistance, we're going to use a capital R, and resistance is going to be resistivity times the length of the wire divided by the cross-sectional area, A. So units, well, it's kilogram meter squared per second cubed per amp squared, or you can also write this as a volt divided by an amp, and we're going to define that as an ohm. So the ohm is our SI unit of resistance with an abbreviation of a capital Greek omega. So the reciprocal of the resistance is the conductance, right? So just like we had resistivity and conductivity were reciprocals, we've got resistance and conductance are reciprocals. So conductance is going to have units of 1 over ohms, and that's known as a Siemens at capital S, or sometimes also called a mho. Notice that mho is just ohm spelled backward. Okay, so once we have resistance, we can define Ohm's law. So remember we talked about that the electric field E had to be proportional to the current density J, or another way to look at that is that the potential difference, delta V, has to be proportional to the current I. So, and that has to be true in general. So if we have a device that's said to be ohmic, then we can define a resistance R that's constant and the same for all values of V and I. So this leads to Ohm's law, which if you've ever taken physics before, you've probably seen Ohm's law. So the potential difference along some circuit element, delta V, is equal to the current through it times its resistance, I times R. Now, an important thing to notice, though, is that Ohm's law, it always breaks down somewhere. So at some point, if the current becomes so high or the potential difference becomes so high, the relationship is always true, but R is not necessarily going to be constant. So, and the most common thing you can have is something called a resistor. So resistors are ohmic devices, which means they have a constant R for all values of I and delta V. So light bulbs, for the currents you're usually interested in, are pretty close to ohmic devices. They're not exactly ohmic, but they're pretty close. And diodes are a type of semiconductor device, and they're very non-ohmic. So, however, so remember, but non-ohmic, so if it doesn't follow Ohm's law, it's still going to be true that delta V is proportional to I at each and every I in delta V. Right? It's just the fact for a non-ohmic device, you don't have one value of R that's always true for all values of V and I. So, and we can actually see this if it's probably easiest to look at a plot, right? So you imagine, so here in the graph here, we're plotting the value of the current versus the potential difference. And these are for ohmic devices, right? And remember, ohmic devices have a constant value of R for all I and V. And on the plot, that just means it's a straight line. So there's a constant slope, right? So if we have a high resistance, then for a high resistance, well, the slope is small. So for a big value of delta V, we get a small current. Now for a low resistance, like the green line, so for a big value of delta V, we get a large current. So it's actually, the slope of these lines is actually 1 over R, 1 over the resistance. So now for a light bulb, you actually see something closer to this. So you'll notice that this is not actually a straight line. It actually has to do with the fact that the filament in the light bulb heats up. But so for V, this actually flattens out. So it's not a straight line, so it's not an ohmic device. So, and here's what you would see for a diode. So, and for a diode, what tends to happen is that you don't get any current at all for, well, if delta V is negative. So if you're trying to push current in the wrong direction, but once you get above some threshold, then the current shoots up very rapidly. So this is a diode. This is very clearly not a straight line. So it's definitely a non-ohmic device.